Greetings, doctor and fellow classmate. My name is Nur Iza, and I'm here today with my teammates Ui Yuan Yi, Poja Meenakshi, and Siti Nurianis. Together, we are here to talk about an incredible important topic: managing limited health budget. Now, why do we choose this topic? Well, healthcare affects us all. It's a worldwide issue involving government all around the world. Let me tell you why this issue is important. First, resources are limited, so we need to spend them wisely. Second, we need to maximize efficiency and equality, ensuring every money is used in the fairest way possible. And we also need to balance immediate needs like addressing outbreak with the long-term goals like disease preventions. And all of this must be done while sustaining the healthcare system for future generations and building public trust along the way. Let's take a look at a real-life scenario. Imagine the Ministry of Health in country that be given 1 million ringgit to improve public health. Sounds like a lot, but here's the catch. They have to divide it into two critical programs. One, vaccination campaign. Two, disease prevention program. This isn't just a made-up scenario, you know. During COVID-19 pandemic, India faced similar challenge where they had to balance between investing in massive vaccinations with strengthening healthcare facilities. So the big question is how they spend this budget in the way that creates the greatest health benefit. Now let's talk about mathematics and how can it help. The objective here is to maximize the public health outcome using this formula where X1 is budget for vaccinations campaign and X2 for disease prevention program. But the total must equal to 1 million ringgit. And then we use mathematical technique called Lagrange multiplier to balance the objective and the constraint to find the optimal allocations for X1 and X2. This ensures every money we spend makes the biggest impact, helping the government make data-driven and efficient decisions. Next, my teammate Yuan Yi will take you through step-by-step of mathematical process to solve this problem.
Let's dive into the mathematical process to solve the healthcare allocation optimization problem using Lagrange multipliers. The goal is to allocate a fixed healthcare budget between two programs. Program 1, vaccination campaign, and Program 2, disease prevention, in a way that maximizes the total health outcome. We will start by defining the objective function and the budget constraint. Objective function. The total health outcome depends on how much money we allocate to each program, since more money generally improves health outcomes, but at a decreasing rate due to diminishing returns. We use a logarithm function to represent this relationship. X1 be the amount of money allocated to program 1, vaccination. X2 be the amount of money allocated to program 2, disease prevention. The objective function that we want to maximize is h x1 x2 equal to a ln x1 plus b ln x2. Here, a and b are constant representing the effectiveness of each program. In our example, we have chosen a equal to 3, meaning vaccination are 3 times more effective than disease prevention. B equal to 1.5, meaning disease prevention is moderately effective but less so than vaccination. So our objective function will be h x1 x2 equal to 3 ln x1 plus 1.5 ln x2. Budget constraint function. Next, we have a budget constraint that ensures the total spending on both programs does not exceed the available budget. Here's our constraint function. G x1 x2 then x1 plus x2 equal to b, where b here is a total spending or budget given. In our case, we assume a total budget b equal to 1,000, representing $1 million. The constraint is then become x1 plus x2 equal to 1,000. Since our equation deal with quantities in simplified terms, we will work with thousands of dollars instead of millions. So we set b equal to 1,000 to represent a total budget of $1 million. In this case, the total spending must be equal to $1 million. Setting up the Lagrange function. Now we use Lagrange multipliers to solve this constraint optimization problem. The Lagrange function is f x1 x2 lambda equal to a ln x1 plus b ln x2 plus lambda in the bracket capital B, which is budget, minus x1 minus x2. Here, lambda is the Lagrange multiplier that enforces the budget constraint. For the above information, which is A equal to 3, B equal to 1.5, and the budget equal to 1000, we can conclude that our Lagrange function is f x1, x2, lambda equal to 3 ln x1 plus 1.5 ln x2 plus lambda in the big bracket 1000 minus x1 minus x2. Carry out partial derivatives. To find the optimal allocation of resources, we take the partial derivatives of the Lagrange function with respect to x1, x2, and lambda and set them equal to 0. For the partial derivatives with respect to x1 and with respect to x2, we solve until getting lambda on the left hand side and let the rest of equation go to the right hand side. Partial derivative with respect to x1, f x1 equal to 3 over x1, then minus lambda, then we set f x1 equal to 0. So our final lambda we will get 3 over x1. This is equation 1. Partial derivative with respect to x2, f x2 equal to 1.5 over x2, then minus with lambda, and we set the partial derivative equal to 0, so our lambda will be 1.5 over x2. This will be our equation 2. Partial derivative with respect to lambda, 1000 minus x1 minus x2 equal to 0, and actually this is a constraint function which is x1 plus x2 equal to 1000, and this is our equation 3.
So let's move on to solving the system of equations. So to do this, we can equate equation 1 and equation 2, which is 3 over x1 is equal to 1.5 over x2, and we will get x1 equals to 2x2. So by doing this, we get like x1 alone on the left hand side. And then we can substitute x1 into equation 3, which is our budget constraint function, which is x1 plus x2 equals to 1000. So it will lead to 2x2 plus x2 equals to 1000, 3x2 equals to 1000, and finally x2 equals to 333.33. So when it equals to that, it means that 333,330 should be allocated to the disease prevention program. And then we can solve for x1 by substituting the value of x2 equals to 333.33 into the equation. So we get x1 equals to 2x2. So we just substitute it by doing 2 times 333.33. You'll get x1 equivalent to 666.66. So when x1 equals to this, it means that 666 and $660 should be allocated to the vaccination program. And when we want to evaluate the maximum value, we want to see the optimal allocation, and we already figured out that 666 and $660,000 has been allocated to vaccination, while $330 and $330 has been allocated to disease prevention. So we can verify this if it maximizes the total health outcome. We can do this by substituting into the objective function. So we can substitute the x1 and x2 into the objective function, which is h in brackets 666.66 comma 333.33 equivalent to 3 ln 666.66 plus 1.5 ln 333.33, and by calculating this we'll get 28.22, which is approximately 29, which means that our total health outcome at this allocation is approximately 29. And then we want to compare this with another possible allocation. So we can, for example, we can take x1 equivalent to 100 and x2 equal to 900. And before we substitute this point, we need to verify whether these new points that we have chosen can satisfy the budget constraint function, which is x1 plus x2 equals to 1000. And then when we check, it says that g 100 and 900 satisfies the budget constraint function because 100 plus 900 equals to 1000. And as it already satisfies, we substitute these values into the objective function, and we will get the total health outcome of 24.02, which is approximately 25. And as 29 is greater than 25, we can conclude that the allocation x1 666.66 and x2 333.33 maximizes the total health outcome, confirming that the value 29 is the maximum. And there are several additional notes that we can say regarding this situation, because the total health outcome is unitless in this model, meaning that the objective function that we're using, h(x1, x2), which is equivalent to a ln x1 plus b ln x2, is representing a relative improvement in public health based on the allocation of funds. And the logarithmic function captures the diminishing returns on spending, but does not assign specific units like life saved or cases prevented, but it is a dimensionless measure of the combined effectiveness of the program. And these constants A and B allow us to adjust the relative importance of each program, but the overall outcome remains unitless because it's used to compare different allocations and maximize efficiency rather than to give a concrete number of lives or cases. So the focus that we have right now is to maximize the benefit in terms of effective resource allocation rather than quantifying specific outcomes in physical units.
In conclusion, this presentation has demonstrated the practical application of optimization techniques to address the critical challenge of healthcare resource allocation. So the summary of the process, which is number 1, formulation of the problem. We define the objective function h(x1, x2) equals to 3 ln x1 plus 1.5 ln x2 to maximize the total health outcome based on allocations to vaccination campaigns, which is x1, and disease preventions program, which is x2. So the budget constraint x1 plus x2 equals to 1,000 ensured resource limitations were respected. Number 2, optimization with Lagrange multipliers. By setting up and solving the Lagrange function, we determine the optimal allocation of 666,660 to vaccinations and 333,333 to disease prevention. So this solution was verified by substituting the values into the objective function, confirming a maximum health outcome of approximately 29. So thirdly, the result interpretation. So the allocation reflects the relative effectiveness of the programs, ensuring resources are directed where they have the greatest impact. So practical application is, this method is invaluable for governments and health agencies during resource-constrained scenarios, such as pandemics or seasonal healthcare challenges. So for instance, it can guide decisions on allocating budgets for flu vaccinations versus broader disease prevention campaigns, maximizing public health outcomes. So the real-life example is, a real-world application of this approach could involve determining how much funding should go toward vaccination campaigns during flu seasons versus ongoing prevention efforts for chronic illnesses like diabetes. So the final thoughts would be, this case underscores the importance of optimization in healthcare economics. So by leveraging mathematical tools, we can make data-driven decisions that maximize public health outcomes even with limited resources.